We're given matrix A and asked to find the eigenvalues and the corresponding eigenvectors. So looking at our notes below, an eigenvalue of A is a scalar lambda such that the determinant of lambda I minus A equals 0. So we need to solve this equation here for lambda in order to find the eigenvalues. And then the eigenvectors of A corresponding to lambda are the non-zero solutions of this equation here, which we'll be solving for vector x. But let's first find the eigenvalues, and I've already set some of this up. Here we have the determinant of lambda times the 2 by 2 identity matrix would be this matrix here, minus the given matrix A must equal 0. Performing the matrix subtraction, notice how we have lambda minus 6, 0 minus negative 3, which is 3, 0 minus negative 2, which is 2, and lambda minus 1. So the next step is to find the value of the determinant, which is this product minus this product, which again must equal 0. So we have the quantity lambda minus 6 times the quantity lambda minus 1 minus 3 times 2 must equal 0. Let's go ahead and multiply this out. We have lambda squared minus 1 lambda minus 6 lambda, that's minus 7 lambda, plus 6 minus 6 equals 0. So simplifying, we have lambda squared minus 7 lambda equals 0. Solving by factoring, we have lambda times the quantity lambda minus 7 equals 0. So notice how we have lambda equals 0 or lambda equals 7. So the eigenvalues are lambda sub 1 equals 0 and lambda sub 2 equals 7. Now that we have the eigenvalues, we'll find the corresponding eigenvectors. And again, we do this by solving this equation here for vector x. Let's first find the eigenvector corresponding to lambda equals 0. So lambda sub 1 equals 0. So again, our equation is here. We have lambda I, which is this matrix here, minus the given matrix A, which is here, times the eigenvector, vector x, equals a 0 vector. Again, performing the matrix subtraction gives us this matrix here. The components of vector x are x sub 1 comma x sub 2, and here's the 0 vector. So for our next step, we'll substitute 0 for lambda. So this matrix would be negative 6, 3, 2, negative 1. Let's go ahead and solve this system using an augmented matrix. So the same system as an augmented matrix would be a 2 by 3 matrix, where the first row would be negative 6, 3, 0. The second row would be 2, negative 1, 0. And now I'll write this in reduced row echelon form. Notice 3 times 2 plus negative 6 would be 0. Let's replace row 2 with 3 times row 2 plus row 1. And to make this element here positive 1, let's replace row 1 with negative 1/6 times row 1. So negative 1/6 times negative 6 is 1. Negative 1/6 times 3 is negative 1/2. And then negative 1/6 times 0 is 0. And now for row 2, we'll have 3 times 2 plus negative 6, that's 0. And then 3 times negative 1 plus 3 is also 0. And 3 times 0 plus 0 is 0. Notice how we have a row of zeros, which means there's an infinite number of eigenvectors. Looking at this first row, notice how this tells us that x sub 1 minus 1/2 times x sub 2 must equal 0. So if we solve this for x sub 1, we'd have x sub 1 equals 1/2 times x sub 2. If we wanted to avoid fractions, we could multiply both sides by 2, which would give us 2 times x sub 1 equals x sub 2. So the eigenvectors corresponding to lambda equals 0 would be vector x, which equals, because we have an infinite number of vectors, let's parameterize this with the variable t. If we let x sub 1 be equal to t, notice how x sub 2 would be 2t, which we could also express as t times the vector with an x component of 1 and a y component of 2. But remember, the eigenvector cannot be the 0 vector, so let's also say that t can't equal 0. Now let's find the eigenvectors corresponding to lambda equals 7. So we'll go through the same process again with lambda sub 2 equals 7. So again, here's the equation we have to solve for vector x. Performing the matrix subtraction gives us this matrix here, and now we substitute 7 for lambda. So 7 minus 6 is 1, so we have 1, 3, 2, and 7 minus 1 is 6. Again, let's write this as an augmented matrix and write it in reduced row echelon form. So the first row would be 1, 3, 0. The second row would be 2, 6, 0. Notice that negative 2 times 1 plus 2 would be 0. Let's replace row 2 with negative 2 times row 1 plus row 2. So row 1 stays the same. Row 2 would be negative 2 times 1 plus 2 is 0. And then we'd have negative 2 times 3 plus 6, that's 0. And of course, negative 2 times 0 plus 0 is also 0. Again, we have a row of zeros, which we do expect. Looking at this first row, notice how this tells us that x sub 1 plus 3 times x sub 2 must equal 0. Solving for x sub 1, we'd have x sub 1 equals negative 3 times x sub 2, which means the eigenvectors corresponding to lambda equals 7 would be vector x, which has an x component of, in this case, let's let x sub 2 be equal to t, and therefore x sub 1 would be equal to negative 3t. If we want, we can write this as t times the vector with an x component of negative 3 and a y component of 1. So any multiple of this vector would be a corresponding eigenvector, again where t can't equal 0. So to summarize what we found the eigenvalues of the matrix A are lambda sub 1 equals 0 and lambda sub 2 equals 7. The eigenvectors corresponding to lambda sub 1 equals 0 are the vectors x in this form here, where t doesn't equal 0. We can also say the eigenspace corresponding to lambda sub 1 equals 0 is given by the span of this vector. And the eigenvectors corresponding to lambda sub 2 equals 7 are the vectors x in this form, again where t can't equal 0, and the eigenspace corresponding to lambda sub 2 equals 7 is given by the span of this vector. I hope you found this helpful.